ice pack.
I am embarrassed to report that I did not simulate the debris. I wanted to, but I did something else, and it's going to look cool. So I hope I can at least deliver something. So my name is Dan Shapero. I'm a research scientist at UW, and I work on ice flow modeling. Brief summary of this. I had this vexing problem for a long time of what do we do in ice flow models about wet and dry states, or ice-covered and ice-free areas, and how do we track the interface between them? And that has bothered me for a really long time. And I think I did something about it. So I'm going to show you how. We'll start in English, and it'll gradually get a little bit more Greek as we go. So I'll start talking a bit about glacier physics. And the thing that I really used here was minimization principles, which I can't really do justice to in a short time, but I'll try and give you the flavor of it. Okay, so just a bit about glacier flow. Why should we study them at all? They're important as a water resource. Everyone knows about sea level rise, but I really like talking about them as a water resource. This is Mount Rainier and the Little Tahoma Peak to the left of it. And what we're looking at is the Emmons Glacier on Mount Rainier. The thing that is all covered in dirt and rock is actually also a glacier. That's also Emmons Glacier. There was a landslide that fell off the Little Tahoma Peak in 1963 that covered 3 different glaciers that all responded in 3 different ways. That's pretty weird. And the White River is in the foreground. It's pretty cold, as I found out. So you could think of glacier flow as a viscous gravity current, and there are loads of viscous gravity currents in the earth sciences: lava flows, debris flows, overland flow. The things that make glacier flow so peculiar are it has an unusual rheology. It's non-Newtonian. It slides over its bed. A lot of the time when you study fluid mechanics, you assume a no-slip boundary condition. And finally, their termini advance and retreat, and they can calve off icebergs. So despite thinking of them like a viscous fluid, they also have this behavior that is characteristic of a brittle solid. So I developed a software package called IcePack for simulating glacier flow. It's in Python. I think it's pretty good. And the goal was to make simulating glacier flow a lot easier and more interactive for people who aren't experts in numerical modeling as such. So it's built on this software library called Firedrake, which is for doing finite element modeling. I think it's really nice. The thing that's so convenient about it is that you specify what problem you solve using a domain-specific language that is embedded into Python. And this has really enabled a lot of the stuff that I've done. It makes for a lot more rapid prototyping, I find. Okay, so glacier flow, how does it work? Oh, whoopsie daisy. So this looks cool. So this is an animation of tracking particle paths through Malaspina Glacier in Alaska that Bas Altena derived from repeat image feature tracking on satellite imagery. And the idea of these big masses of ice as a fluid is kind of hard to conceptualize, but I think this kind of illustrates it really nicely. So a typical mountain glacier, you'll see speeds that are on the order of, say, 100 meters a year is typical, just to give you some sense of the numbers. Okay, so the basic principles we're working with are mass, momentum, and energy conservation. And I've just shown the mass conservation equation here. So ice is nearly incompressible. So you integrate that in the vertical, and you get a transport equation for ice thickness. I'm not going to focus on this so much. I don't want to underplay how difficult it is, especially estimating the accumulation and melt rates and how those relate to climate and elevation. But mostly what I'm going to talk about is the momentum balance equation. So the first principles model that we use for momentum balance are the Stokes equations, which are a balance of viscous stresses, pressure gradients, and gravity. But what makes ice so unusual is that its constitutive relationship is not linear. So for a normal fluid like water, stress and strain rate are linearly proportional to each other. But for glacier flow, from some lab experiments, people found that the strain rate is proportional to a power of the stress, and that exponent n is usually thought to be 3. There's a very loud team n equals 4, and really it's probably several powers. Some people think 1, 3, and 5, and other people think 1.8 and 4, and they get into very strangely personal arguments about this. The constant there depends on temperature. It also depends on all sorts of other things like dust. The atmosphere of the last glacial period was dustier, and that makes the ice easier to deform. So this was originally derived from lab experiments, but we see it in field data. So this is a finite element simulation that Charlie Raymond did 5 years before I was born, and where he was showing what the particle paths do when you assume ice flow is just purely Newtonian versus non-Newtonian, and that the constitutive relationship affects the paths that particles take. And we see this in field data. So this is a radargram from Antarctica. And the shape of the isochronous layers near the bed is an indication of that nonlinear flow law, which I think is pretty cool. Okay, the other missing piece is the sliding law. So what is happening at the ice base? So again, people say, I don't know, maybe it's a power law. And that exponent m, in some regimes, they think that it's the same as the flow law exponent. In others, it's much higher. This is much more hotly contested. So that's a function of the geology and the hydrology under the bed. And again, pictures are nice. So this is an image from northern Canada where we can see the scars on the landscape from the Laurentide ice sheet. Okay, so the first principles model we use are the Stokes equations, but in practice, no one ever really works directly from the Stokes equations because they're 3D and they're much more challenging. So what people always try and do is use perturbation theory to simplify them. The first step you do is most glacier flows are very thin. So this gets you to a simpler set of equations. And from there, we have two diametrically opposite approximations that we can use. One of which is that all flow is by deformation in the vertical. So it's the xz and the yz components of the stress tensor that are important. And in the other, it's the remaining, the xx, xy, and yy components of the stress tensor. So the one on the left, the shallow ice approximation, is where the flow looks like this. And the one on the right, the shallow shelf approximation, is where the bed and the surface are moving at the same velocity, but all the stresses are from extension in the horizontal plane. So here's another figure to kind of illustrate that. And it's just important to note that we have two models that are nice to compute with, and they work in totally different regimes, and that's quite aggravating. How good do they actually work? This is a paper from 10 odd years ago. Katie and I overlapped during our PhDs, and they hauled a terrestrial radar interferometer up to Mount Rainier, and they found that it was flowing at about 200 meters a year at Emmons Glacier, the one that I showed in that earlier slide. And the shallow ice approximation predicts a velocity of 10 meters a year. So that's not awesome. Why do people do this? So the shallow ice approximation, it works fine with dry states. So that's certainly something that it has to its credit. And so that's the reason why people have used it so much for mountain glaciers when they want to study their advance and retreat in response to a changing climate. But they do a really poor job predicting ice velocities as soon as they're sliding because they cannot incorporate any longitudinal stress. The shallow stream approximation, on the other hand, it can get the velocities right, but it just goes all to hell as soon as the ice thickness is zero. People do the sort of dirty hack where we assume that the ice thickness is bounded below by some constant, and that creates all sorts of problems. So this is sort of the dilemma that we're stuck with, is we have two models, and the trade-offs between them are not great, and you sort of just have to pick one. And this bothered me for a really long time. And I thought, wouldn't it be great if there were some way that we could get the nice properties of the shallow ice approximation, namely that it works even with a dry state, and have that same characteristic of the shallow shelf approximation. And I believe that I succeeded, and I'll show you some movies to convince you, but it involved scads and scads of math. So here we go. So there's I'm going to write out more of the math here. The important variables to make note of are the ice velocity, u, which is mainly what we're solving for, and the membrane stress tensor, which I've written as capital M. And that's what's left over from the deviatoric stress tensor after you make a thin film approximation and depth average it. So you can think of that as containing the role of what the stress tensor does normally in 3D. So the shallow stream approximation, like the Stokes equations, is a conservation law, but for membrane stress instead of deviatoric stress. And it is a balance between stress divergence, friction at the base, and gravity. And here gravity is thickness times the gradient of the surface slope. Ice flows downhill. And so again, we have to supply the constitutive and sliding laws. And I've written out more of the math explicitly here. But if all you remember is, again, the strain rate is proportional to some power of the membrane stress instead of the deviatoric stress, then that's really enough to understand the rest. And finally, the sliding speed is proportional to a power of the basal drag. Now, okay, fine. So we have all the ingredients. We have a conservation law, and we have two constitutive relations. So we invert those. So we go back and we isolate the membrane stress as a function of strain rate. We go back and isolate the basal drag as a function of sliding speed, shove those into the momentum conservation law, and put it in your finite element solver and utter a silent prayer that it converges. And that's good, right? Well, I submit that there's quite a bit more we can do. So there are certain special classes of differential equations that can be derived through minimizing some scalar quantity. This is kind of cosmic, and I can't really do justice to it here if you've taken Lagrangian mechanics. This is similar to the stationary action principles you might have seen. When a mathematician tells you something is cool, you kind of need to be skeptical because by and large, we're just in it for the aesthetics. But this actually does change the kind of code that you can write. You can write solvers for problems that have minimization principles that are where you can make sure that they're almost always guaranteed to work. And for me, I really care about this because I want glaciologists to not be annoyed with me and say, hey, the solver crashed, like, can you help me? This thing works like garbage. What are you even doing? Now they say, wow, this thing works all the time. I don't even have to think about it. That's really what this enables for me. So the simplest minimization principle is for elasticity, where when you're solving the equations of linear elasticity, really under the hood, you're minimizing the elastic energy displacement. This is funny because viscous fluid flow is a dissipative problem. And so it strains that it should also have a minimization principle, and yet it does, and we can do cool things with this and write better code. So just kind of roughly in English, what is the thing that we're minimizing when we're solving the shallow stream approximation? It's a sum of several terms, one of which comes from viscosity, friction, and gravity. And what it looks like is we're averaging the strain rate to the power of 1 over n plus 1, which is basically 4/3. And the other important thing to note, the thing that we're minimizing, so it has units of power as an energy per unit time, which if you've taken statistical thermodynamics, it's the rate of dissipation of free energy. So I'm going to refer to it as the free power in the following. And just a little bit more Greek if you like that. But again, the details are mostly unimportant. The picture that I think will help is looking at what the free power density is as a function of strain rate. Well, so it's the strain rate to the 4/3 power. And I want you to just focus on the left-hand plot here. So really, I'm just plotting epsilon to the 4/3 on the left here in blue. I'm going to explain what's going on in the right-hand figure in a moment. But the thing to notice is that this has a cusp around 0. And I don't have a proof of this, but I think that's really where a lot of the headache comes from when the ice thickness is equal to 0. So I've shown in orange the curvature of that line, and it goes to infinity around that cusp. So when the ice thickness goes to 0, the strain rate is also going to 0. And so what's happening under the hood on your little CPU is you're trying to multiply 0 times infinity, and you're having a bad time, which maybe isn't so surprising. And I'll explain how we get to the thing on the right in just a moment. So that was kind of where things stayed for a while, and it was generally sad, and I had no idea what to do. But what I would really wish I could do is, simulate things like this, where there are glaciers that are calving into embayments. And there's ways of doing this using interface tracking methods, but I don't understand them, so I didn't want to try. And I really just wanted, is there some way that I can rewrite the shallow stream approximation so that I can still solve it even when the ice thickness is 0? So the dilemma here is the shallow ice approximation works with dry states and the shallow shelf approximation doesn't. Is there some hypothetical model that has the good properties of both? And I tried for a long time to figure out what it was. So I had this postdoc advisor, and he was an expert in convex optimization. And he always kept talking to me about something called convex duality. And I never understood him, and I still don't. I asked people once who are mathematicians, hey, how could you explain convex duality to someone who doesn't really know about it? And usually they just laugh in my face. So I don't get this either, but I was able to operationalize it to do something useful. So hopefully that convinces you that maybe it's worth knowing about. So every minimization problem has a twin. And it's possible that you only ever got to know the evil twin, and that actually the good twin is out there somewhere. And I submit that the original form of SSA is actually the evil twin, and I have located the good twin. So Sasha, my postdoc advisor, kept telling me about this, and I worked out with a convex. Oh, sorry, there's one more thing I should say. There is a rote mechanical procedure for deriving what the twin problem is from the other problem to derive the primal from the dual. So even if you don't understand the stuff, you can go through the calculations. It's basically no harder than evaluating the antiderivative of a function. So I sat in a cafe at AGU once because I was tired of listening to talks, and I had a big cup of coffee, and I worked out what the convex dual of SSA was, and then I lost the notebook. And there was some trick in the algebra that made it go, and I couldn't remember what it was. And it was like years before I remembered it in like the neonatal ICU when my son was born. Anyway, so then I figured that out again, and now here we are. So the important part about the dual form of any physics problem is that it inverts all constitutive relations. So in the primal form of elasticity, we express stress in terms of strain. In the dual form, we go the other way. We express strain in terms of stress. Before, I wrote down the strain rate in terms of stress with that nonlinear constitutive law. But when we use the primal form, I have to go flip that around to get stress in terms of strain rate. And there I get those powers that are less than 2. When we go to the dual form, we flip the character of all of the nonlinearities. And I think that's what really saves us. So now we get rid of that problem that I mentioned before of trying to multiply 0 and infinity and having a rough time of it. Here's the Greek if you want it. So before I had a strain rate to the power of 4/3. Now I have membrane stress to the 4th power. And the difference between powers being less than 2 or greater than 2 is really what I think makes all of this go. So I showed you this figure before. On the left is the free power density as a function of strain rate. On the right, I have the dual form showing the free power density as a function of membrane stress. So whereas before there's a cusp, now it goes flat. Before, the curvature goes to infinity, and now the curvature goes to 0. That's also bad, but it's a form of bad that I can work with. I can negotiate with 0. I can't really negotiate with infinity. In case that was all total nonsense, it worked. And I had a collaborator, Gonzalo Gonzalez de Diego, who's wonderful. We wrote a paper about this that came out last year. So this is a simulation. I'm showing the thickness of the Larsen C ice shelf in the Antarctic Peninsula. And we forced it to reproduce the big calving event that happened there in 2017, where it broke off an iceberg the size of Manhattan. This is another one from that paper where I was showing the evolution, again, of the thickness of Kangerlussuaq Glacier in southeast Greenland, where we were able to make the terminus move back and forth with a mass balance at the front that we kind of forced it to take so that it would have roughly the right seasonal behavior of advancing and retreating. The shape of the terminus there is not right. It should be kind of the other way. And so one of the new things I'm working on is how do we supply the right calving law that can give it the correct shape? The final thing that I think is going to be most interesting for folks here, my student John Maurer and I have been working on using this for mountain glaciers. So this is a simulation he made of spinning up the thickness of the Emmons Glacier towards some steady state based on some initial very goofy estimates of the thickness. And he's able to reproduce a lot of the features that we actually observe. One of the interesting things about the Emmons is that it's covered in debris. So he did a lot of work on what is the right surface mass balance to put in. So debris is funny because it's black. So it enhances melt at low thicknesses, and it inhibits melt at greater thicknesses. So it's weird because debris-covered glaciers are longer than you would expect them to be just based on the climate. And so he did a lot of work on that. And here again are some of his simulations. So this is the thickness and the ice velocity that he found. And with this funny new dual model, we're able to get velocity maxima and minima with the seasons that are the same as what we observe. So I think that this is at least a viable model that can get the speeds right, which the shallow ice approximation cannot do. And it can have an advancing and retreating terminus, which the primal form of SSA cannot do. So I'm pretty pleased with this. John is writing this up now, and that's going to be one chapter of his thesis. And we talked to someone at Cal State San Bernardino. Her name is Claire Todd. And I talked to her for an hour, and she convinced me that I should just become a field glaciologist. And she's very convincing, and I thought, yeah, that sounds totally reasonable. And then I got off the phone with her, and I thought, what did I just agree to? So we went there. And that's one of the tributaries of the White River. You'll notice the bridge there that isn't up because the park was still closed. So we had to drag $40,000 of radar gear across that very cold river and get up over that moraine. And then we bushwhacked through an unholy amount of slide alder. And you can see the terminus up there is all covered in debris, and haul all of it up over that moraine. And this is cool because we can see the ice through the debris, which I thought was pretty neat. And we were starting to get frightened by all the very large boulders that were extremely easy to mobilize, and we didn't want to have any injuries. So we found the first patch of snow where we could put the radar. John is a very, very, very good mountaineer. I'm kind of a filthy casual. So I felt bad about, getting my graduate student to do all the probing and the safety stuff, but he knows a whole lot more than I do, and he was comfortable with it. So he made sure that we weren't going to fall in a giant hole. And we were able to, so this is the radar system, which is on wheels, which is not optimal, but it was what we were able to borrow. And so we were able to deploy it there, and we found that there was 150 feet of ice underneath us. So we were able to image through this ice-cored moraine. And that all came in parts, and we had to, take it apart and put it back together, and many of the parts are very bulky. I wanted to end with this. So these are 3 melt channels from under the glacier that then feed the White River. And 2 of them are blue, and 1 of them is brown. So the suspended sediment in one of those melt channels coming out from under the glacier is high, and in 2 of them it isn't. And that's weird. Maybe you all know. I just thought it was neat. Okay, so kind of conclusions. Minimization principles are really cool. If you ever go out for drinks with me, I'll talk about them at some point because I'm very fun at parties. But they can make a lot of really, really heinous problems doable. And so it's just a thing that's worth looking into. There's many different ways to express the same physics problem. Some of them are more advantageous than others. So there is value to be gained out of trying to rethink what is the problem you're trying to solve in the first place. Okay, final thing. I have a proposal for a paper, and I've wanted to write this for a long time. So Greg in his clinic showed a figure from Josh Roering's paper about the nonlinear hill slope transport model. So there's mass flux from hill slopes that is a function of its surface slope, but the flux goes to infinity as the slope approaches the critical slope. And this has a minimization principle, and I've never seen this published before. I asked Greg, I've asked Josh Roering, I've asked other people. I don't think anyone has seen this before. I think that's kind of cool. That to me just sounds interesting, and there's probably cool numerics we can do with this. So just showing you the free power as a function of slope. It goes to infinity once you approach the critical slope. And I definitely have not seen this, which is that there's a dual form of that same free power, which doesn't go to infinity, it goes to a constant slope. So before, the curvature goes to infinity. Here, the curvature goes to 0. And you can negotiate with 0, you can't negotiate with infinity. So I think there's some cool numerics that we can do with this for nonlinear hill slope transport. I've been trying to get this together for a while, but I'm not a geomorphologist, so I don't know, help me do it. That's all.
Yeah. Dan could not get that in the Mentimeter, that last proposal, but he's got a speed dating page set up here. Are there
questions?
Other questions? We have time for one question, or we're making time for one question.
Wolfgang?
So I like these analogy things, but I'm not crazy on it because I understand about as much as you do. But about the glacier, so you showed a picture of the glacier that comes from the corner, right? And it does not actually solve ice cap. Just the collection of ice boulders is the one that probably ride on a thin layer. How do you model those? Because something like this.
Right, so your question was, so you mentioned specifically the ice riding over some kind of unconsolidated sediment or boulders underneath it. Oh, okay. Yes, so it's a good question to ask whether the continuum assumption is even an assumption that you should be making for this type of problem. And by and large, people just kind of keep doing it and hope that it's okay. There's other models that have tried to use, so Elmer has used discrete element models to simulate iceberg calving. And I don't know of anyone trying to use that for kind of more of the interior of glaciers where they're heavily disturbed by crevasses. Often what people do is some kind of effective field theory where they introduce a damage field that is supposed to account for that. That's very much like frontier research is what you should do there.